Hello everyone. It's very happy you are here to listen to the tutorial about deep learning for dialogue system. And I am Chen, and this is Asli, and I'm from National Taiwan University, and Asli is from Microsoft Research, and this is Dilek. Dilek is from Google Research, and we will take turn to present the tutorial. Okay. So this is the outline of this tutorial, and we will have a short break in the middle of the tutorial. And also, if you have any question for discussion, you can ask them in the end of the tutorial, or if your question is about the clarification question, you can directly ask this question during the presentation. Also, we will have the online material here. I'm not sure whether you can see it clearly. The URL is deepdialog.mulab.tw. And also, for different, we collect a lot of research work, and we will put the archive link here in each work, and you will directly click the link to access the paper if you are interested in. Okay. So I will give the introduction for the dialogue system. So from the history of the dialogue system, we will talk from the very early 1990s. Like there are some task-specific extraction. They usually use the keyword spotting. Like if the user mentions some keyword, like the phone or some task, and we will detect the keyword and design the following associated actions to the users. So this kind of interaction appeared very earlier. And also, this is very difficult because we are not have enough data to do the training, and also we do not have this human computer interaction. So in the early 2000s, we have some multi-model system. The goal is try to decide the intent of the user and use different modality. So recently, we have different interface like the smart TV or the smart watch, and we can use the speech to do the communication or to do the search. And a lot of people are interested in the virtual personal assistants. Like there are several different types of systems released by different leading companies like Apple, Google, Microsoft, Amazon, Facebook, and there are so many different types of virtual intelligence systems, which is all about dialogue system. We want to help users to finish certain tasks. But why we need them? We need to consider if we see our daily usage of our smartphone. Like we get a lot of things done using our smartphone. Like we set an alarm or reminder and take notes. And we also access our structured data like the photos or the document like the notes we previously took. Also, if our smart device can understand you very well, they can assist your daily schedule. Like they will remind you this time you need to go out so that you won't be late for your work. So the ultimate goal is to be more productive in manage our work or personal life, because life is very limited. So a lot of busy person will hire a human assistant to do this busy task for them. But not everybody can afford a human assistant, so we want to have our own virtual assistant to do this task for us. This is our dream. And for natural language, we can use different type of interaction, but why we want to use natural language? And from 2 years ago, there's a statistic show that the global population is around 7 billion, and there are 3 billion people are active internet users. And also 2 billion people are active social media accounts. But if you see the number of active unique mobile users, which is around 3.65 billion, the number even more than the number of active internet users, which means users move their interaction from the World Wide Web to the mobile device. So in this device, the more natural and convenient input evolves towards speech. So that's why natural language is important. That's why we are attending ACL. So in a dialogue system, the formal definition is dialogue systems are intelligent agents which can help you to finish tasks more efficiently via spoken interaction. And this kind of system are already incorporated into different devices. For example, the smart TV, smart phone, or the navigation system. There are two famous movies including the task-oriented dialogue system, like Iron Man's drivers. They can help Iron Man to fix some component or download some document. And Baymax focus on the healthcare domain, try to provide a suggestion for the user. So we know that if we can have this good dialogue system, we can easily access the information and also finish tasks, just use the conversation. So if we think about we use the app daily, we can also change the app interaction into bot interaction. So a bot is responsible for a single domain, just like an app. You can imagine that. So this is the app for the haircut reservation. Like you need to follow the GUI design and click the like if you want to do the haircut, you need to click the corresponding item and also type the date you want to do the reservation and the time and the number of people. But if you use the bot, you can initiate the dialogue by your own, like haircut on Saturday, and the bot can automatically understand your intent and try to provide you the information you are looking for, like the information about time, and then you can do the reservation easily compared to the original GUI design. Then user can have their own dialogue. So compare these two, GUI and CUI. CUI means conversational UI. Like the GUI usually is allow the user to browse the information, but CUI is allow user to ask the specific information. So between these two different type of interface, the difference is like the GUI display the more information, but the CUI can have more precise information, and also the manipulation interface is different. The CUI use the language to do interaction. You can use text or speech as input, and also it's very easy to learn because it's just like to talk to other people like your daily life. So the entering boundary is lower than the GUI. So it's also easy to incorporate into different message-based interface. So they have higher flexibility. But there are several challenges in the dialogue system. For example, the variety in natural language, and also our system need to care about the robustness. Also, how can we balance the recall and the precision issue? And we do not have very good or the clear meaning representation for the dialogue system currently. And if we want our system can understand us, they need to understand the common sense, like the word knowledge, in addition to only the conversation we mentioned before. So, and also the system should be able to learn information day by day, and also transparency is also an issue. So here we find that there are two different branches of bot development. One branch is about task-oriented bot. Another branch is chit-chat bot. Task-oriented, just like a personal assistant, which help user achieve a certain task. This is our focus for this whole tutorial. And I will mention a little bit about the chit-chat bot. So for the task-oriented dialogue system, usually the goal is to accomplish certain tasks, and they combine a different type of rules or the statistical component, and just like the Iron Man's Jarvis is a task-oriented bot. And another branch is chit-chat bot. Chit-chat, they do not have the specific goal. It focuses on natural response. So there are several different types of sequence-to-sequence model for generating the dialogues. And this is the Microsoft Shell Ice, which is the chit-chat bot. They do not have the specific goal. They just provide the natural response for the user. But recent research, they have some work between these two. Like chit-chat bot want to have more knowledge, and task-oriented bot want to have more flexibility to do the chatting. So we are finding the balance between these two different branches. So in the task-oriented dialogue system, okay, this is the link we showed according to the paper we cite. In the beginning, if we have a speech signal, we can have the speech recognition to recognize the speech into text. Also, the user can directly type the natural language into this system. The first important component is language understanding. This one is try to extract the semantic frames, which include the domain and user intent and also associate slots. For example, are there any action movie to see this weekend? Based on this input, we want to extract the user is focusing on request movie, and the constraint about the movie is general is equal to action and date is equal to this weekend. And another following component is the dialogue management. In addition to extract the semantics, the system need to understand the current dialogue state within the whole conversation and to decide what actions to select in order to finish the task more efficiently. For this example, the system select the action which is request additional constraint about location and send to the natural language generation module to do the interaction to the user. And the second term, the user will respond the location information and go back to the system iteratively. So let's see an example. If you want to find a good eating place for Taiwanese food, so we assume the system can answer good Taiwanese eating place include Din Tai Fung, blah blah blah. What do you want to choose? So let's see how does the dialogue system process this request. First module, understanding. The first one is very easy, like we want to decide which domain database we need to do the search in order to get the user's answer. So for this one, it's about the restaurant. So we just do the sentence classification. It's pretty easy. And later on, we need to decide the intent. Like based on this domain, this database provides several operations, like they can find restaurant for you, or find price, or find the restaurant type. So we also do the classification to decide based on this sentence that the user want to find a restaurant because they want to find a good eating place. Afterwards, we also need to extract the slot values, which means the constraint about the find restaurant. So in this table, this is the database. So we have different restaurant and different attribute of the restaurant, like the rating and the type. So here we want to extract, they specify the rating information and also the type information in the original sentence. So if we can extract this information, we can construct this semantic frame and convert into a SQL query to do the search in the database, so that we can have the result and return to the user, or decide the next action and then return to the user. So how can we do this? This one is usually done by some sequence labeling. For example, we want to tag each word with the semantics value for semantic slot. For example, O means out of concept, B means beginning of concept. So good means this is the beginning of rating, and Taiwanese is beginning of type, which is the BIO framework. After understanding the semantics, dialog manager needs to decide the state in the current conversation. So, how to do that? So we can imagine in the beginning of conversation, the dialog state is in the null state. And if the user specify good eating place for Taiwanese food, they specify the rating and also the type. So we can imagine at this time the conversation already moved to this dialog state. And if the user further constrain the location, we can imagine we already proceed to the final dialog state. So this is the optimal path we want to track during this simple two-sentence conversation. However, it's very difficult. Because they have very noisy input, it could be find a good eating place for Thai food. It's not clear this is the correct answer, right? But it could be possible to extract the Thai food for the type. So if we can estimate the conversation is also in this dialog state, but it's difficult to decide which one is the correct state for the value of the type. And it's possible that this understanding module cannot extract the type information. They just extract the rating. So we cannot understand which one is the best dialog state for this current conversation. So only one sentence we have a lot of ambiguity to decide which dialog state we are in. So usually we'll have some probability estimation over the whole dialog state, and we'll go into detail in the later tutorial. So after we get the estimation about the dialog state, dialog policy is to design for the system which actions to select in order to finish the task more efficiently. So here we can inform the information to the user or request additional constraint or do some confirmation. Like if we are not sure about the value, we can confirm this information by the interaction. And then feed into a natural language generation module. So generation module is try to generate the natural language or the GUI output. Like you can inform information using natural language or just display the information on the screen, as well for request and confirm. Okay, so I want to briefly talk about the background knowledge, although I think everyone already familiar with. Okay, so for neural network, like machine learning is like to learning a function for speech recognition, like transfer the signal into a text, and image recognition transfer the image to the category, or go playing transfer the go board into the next move, or chatbot, where is the last thing we want to answer the address is. So machine learning is like given a lot of data, we want to learn what the function f should be. So this is the machine learning area, and deep learning is type of machine learning approach called neural network. I think everybody familiar with it. So a single neuron given a vector of the input x in left hand side, the single neuron try to do the weighted sum of the each value of the input vector and fit into the activation function, and we can have the y between 0 and 1. So we can adjust the w and b and to adjust the value of y. So a single neuron, for example, if we want to do the image classification, like this is the image, we can transfer it into a vector, and we can adjust our weight to allow if the image belongs to digit 2 and y can be higher than 0.5. Otherwise, this image is not the digit 2. But a single neuron can only handle binary classification. How about the multi-class? Like we want to recognize different digits, so we can just have 10 different neurons to handle the 10 different class. So we compare the next one to decide which one is the most possible digit this image belongs to. So deep neural network is try to stack several layers of neurons in order to get a more complex function. So deep neural net means they have multiple hidden layers. And recurrent neural network, we will use it a lot in the later tutorial because usually we need to model the temporal information. They can accumulate the information using a time sequence, like we care about the order of the word within the sentence. So we use it a lot. Okay, so another important approach is the reinforcement learning. What is reinforcement learning? Which is the general purpose framework for decision making. Usually we have an agent which have the capability to do the action, and the action will influence the agent's future state. And we will measure the success using a reward signal. The goal for the agent is try to maximize the future reward. It's a little difficult to understand, but we can show a scenario using AlphaGo, very famous one. So based on the observation for the Go playing board, like the AlphaGo will select the action which is next move about this Go game. And the goal is to try to, the reward definition is if the AlphaGo can win this game, they can get a positive reward. If lose, it gets negative reward. If haven't finished the game, they just get a 0 reward. So the goal for the agent is try to take actions which can maximize the future expected reward. So they want to maximize the probability of winning this game. So this is the reinforcement learning. Compared with supervised learning, using the dialogue system as an example, if the user say hello, you just teach him you need to say hi. And if the user say bye-bye, you just teach him you need to say goodbye. This is a supervised learning. But what about reinforcement learning? You just allow your agent to interact with the user. And after the interaction, they will get some signal. If they get a very bad signal, they will try to adjust their dialogue policy and to improve itself. So it's called reinforcement learning. So supervised learning is like learning from the teacher. Reinforcement learning is like learning from critics. But because this is a decision-making framework, but it's very difficult because the goal is try to select actions turn by turn, but the actions may have long-term consequence, and also some reward may be delayed. Also, it could be possible to sacrifice current reward in order to gain more long-term reward. So it's very difficult for the neural net to learn the information. So for deep reinforcement learning is use the deep neural net to model the reinforcement learning agent. Like the function input is the observation of this environment, and the action is the function output. We want to learn this neural network. And how to learn it? We base on the reward function and try to pick the best function to do the better input and output alignment. Okay? For the reinforcement learning, usually they will start at the initial state and choose the action A0, and they will proceed to the next state, like S1, and continuously. So total reward, which is like our goal is try to estimate, like maximize the expected total reward, like from the current state until to the final state. So there are several different types of approach. One type is about policy-based reinforcement learning, which means we want to search the optimal policy, which means this is the policy which can achieve the maximum future reward, like the actions they want to do. And another one is the value-based reinforcement learning, which means we want to estimate given a state S and a action, and we want to estimate the value we can achieve for this state and doing this action. So this is a little different from the policy approach, but it's related. So they also have the fused approach, including policy and also value-based approach. And another one is the model-based. Model-based means we want to have a model to mimic the environment, and we can do the planning in advance so that we can select action because we already look ahead the possible environment change. Okay, so for this is the task-oriented framework. So we will dig into the detail of the language understanding, dialogue management, and natural language generation module. So I will give the microphone to the Dilek. She will talk about the next part.
Thanks, Vivian. So, okay. So in this part, we want to briefly review the recent literature on goal-oriented or task-oriented dialogue systems, and then move on in the next part to the further. But in general, for goal-oriented dialogue systems, the setup is like this. User has a goal in mind. They want to achieve this goal, but they don't have access to the information. The system doesn't know the user's goal, but it has access to the back-end information. And through interactions with the user, it tries to understand what the user tries to achieve, and then informs the user about things so that they can actually negotiate and try to find a solution to the user's goal. So in this, the most common architecture, as Vivian has been describing, is basically first step is like recognition, but then language understanding, which takes the transcribed sequence of words, transcribed user utterances, or maybe the ASR lattices, and then converts them to some internal representation. So this internal representation is usually designed or optimally designed according to the backend information sources. So there can be this interaction. And the goal of dialogue state tracking is doing this, what language understanding is doing over a single turn, over multiple turns, and accumulating the user's goal, and then looking up the backend, and then informing the user about the interim status of the goal. So then the dialogue policy, it just basically tries to determine what the optimum action should be. So for example, given the information, if the user's, even the temporary information, if the user's goal is not satisfiable, it's supposed to go back and then give options to the user. Or if there is something that is satisfying the user's request, then it should offer them as options, as possible options. But then what the policy does is it basically outputs the action in, again, its internal language, and then finally the NLG generates the natural language text that the user can understand. So the backend, and then the definition of the backend actually kind of seems limiting, but then the backend, it doesn't necessarily have to be a single thing. Imagine the cases of multi-domain dialogues. Then this system can actually do things. I mean, imagine it can actually do things that would be even difficult for the humans to handle, especially if the users have goals that are satisfiable by that are in multiple domains. For example, planning a night out, or like going on a trip, but you want to buy plane tickets, hotel, etc., etc. So this promise of the dialogue systems that they can actually do things that are even more difficult for human agents to satisfy, very simple. And being able to do this in natural language is, I believe, the most interesting thing about the goal-driven dialogue systems. So now let me move on to the components. So I'll start with language understanding. So language understanding in goal-oriented dialogue systems has been mainly seen as a triage of three tasks: domain detection, intent classification, and slot filling. And the first 2, domain and intent detection. These are basically utterance classification problems, meaning you are given a sequence of words and then you need to decide on one or more labels that could be assigned to that utterance. So, for example, if it is domains, if somebody says, find me a cheap Taiwanese restaurant in Oakland, that implies the restaurant's domain, and each of these domains have multiple intents, and the intent on the, I'm not sure if you can see my cursor, but maybe not, should use this. On the right we list a possible set of intents, and then this one is basically implying finding a restaurant. And the way these classifiers are trained is they are basically given a sequence set of utterances paired with gold standard labels for domains and intents. And then the goal is when a new user utterance comes in to estimate what the domain or intent of that utterance is. So, starting like in a little bit earlier work on domain and intent classification, one of the first studies that used deep learning for this task was IBM. But what basically had is a deep neural network. So that neural network originally was trained from utterances to utterances. It was an RBM, and a set of weights were trained in this fashion, and then these were then plugged into a higher level, top level, which has the class label units. And then finally it would estimate, the weights would be trained to estimate the categories for each of these utterances. And this work basically compared this approach. So up until that time, around 2011, all of these methods like boosting, support vector machines, maxent were in use, and this work basically made some advancements over them. And the next work, which is along very similar lines, is again a deep neural network. But in this case, instead of just having a flat hierarchy, the lower level would just get the sequence of words as input, and then the upper levels would get both the estimation from the lower layer plus the input data again and again. These are called deep convex networks. And in this work, basically, the utterances are represented as a bag of features, where the features are estimated using some salience measures. And later on, authors extended this type of networks to kernel DCN, which would actually have kernel methods in the middle. So moving on, not only deep neural nets were used for utterance classification, but also more recurrent architectures. For example, this work by Raouri and Stoke. What they do is they get a sequence of words, and it's an RNN. Basically, at each timestamp, they consume one of the words, and there is a hidden layer and then an output layer, and the output would be at each timestamp the class label. Of course, these can disagree with each other, but you can always take the majority or another measure. They also tried outputting the utterance class only after the last token is consumed. And they again compared this with the earlier methods. So, moving on, more recently, again, RNNs plus this time CNNs also for dialogue act classification. So this network is very similar to the previous one. So words are consumed, and the hidden layers are basically pulled at the top level to output the final class. And this architecture was compared with a convolutional neural net, which would basically get word n-grams as input, and then again there is the pooling layer. So, on the contrary, slot filling is basically a word classification, is viewed as a word classification task. So, given an utterance like flights from Boston to New York today, the goal is to estimate a tag for each of the words in the utterance. So, you can represent the tags as inside-outside beginning, meaning, so New, for example, is the beginning of arrival city name, and York is inside the arrival city name, but to is not a member of the slot. So given the sequence of words, the goal is estimate to this sequence of tags. And the training is basically done, or could be done in a supervised fashion. Imagine you're given a sequence of words and sequence of tags associated to the sequence of words, and you train a model to estimate the tags for new incoming utterances. Work on slot tagging basically started with recurrent neural nets, and again at each timestamp you're inputting a word, and then there is a hidden layer which are connected, which provides embeddings to the next hidden layer, and then the output is the sequence of tags. And this work was basically extended to not just input the individual words, but also word windows at the lower layer. So this would be taking like an n-gram window and then sliding it over the input and then providing it as input at each timestamp. So in this case, you can imagine you can pad the beginning word with some padding tokens, and then the final words with some padding tokens as well. And bidirectional LSTMs. So this is training a recurrent neural network in two directions. So one of them would go from left to right, the other one would go from right to left. There are two hidden layers basically. And then the output layer consumes the two hidden layers, concatenated or added, and outputs to tags associated with each word. So you may imagine, like, why is this obsession around using context? So slot filling tag is the context of the words is very important for this task. So the earlier methods basically mainly focused on how can we integrate the context in so that we can parse these utterances. And moving on. IBM team tried encoder-decoder style networks. So in these ones, you wouldn't start outputting the tags till you consume all the words in the input. But a trick that they played is actually presenting the words in the reverse order, which seems to make a difference. You consume all the words, and then when you get to the end of the sentence, you have basically a token that says, okay, now you are at the end. And then the decoding then starts. Again, there is yet another set of hidden layers. And then the words are input again. And then the goal is estimate the tags after you have an embedding of the whole utterance, which is coming in from here. Another extension of this is actually using an attention model. So what does the attention do? Basically, it's a very similar network to the previous one. But instead of, in addition to getting the hidden layer from here, what this approach does is it basically estimates an attention over the input word. It aims to estimate an attention over the input words. And this attention is estimated using the corresponding hidden layers and then also the hidden layers on the decoder side. And then it's input to the network. In addition to the words, it's input to the network. The goal here is usually, again, to capture like longer distance context or from both sides of the word. And moving on. So there have been studies basically trying to do multitask learning. What does this mean? Basically, if you have multiple domains or multiple tasks, imagine you have utterances from movies, restaurants, hotels, etc. You can imagine some of these slots could be shared between these different domains. For example, both hotels and restaurants will have a date, or movie and restaurant would have the time information. So similarly, many natural language processing tasks do actually share information. For example, phrase boundaries, you can probably learn them from the abundance of parsed data that is out there, and then benefit from it when you are doing something like slot tagging. So multiple teams tried doing multitask learning, which is very similar to the bidirectional LSTM I described before. So there are two hidden layers going in each direction. But then on the output side, the output layer is not shared between two tasks. So you train the lower layers so that you transfer information from one task to the other. And this has been shown efficient, especially in the cases of multi-domain CLU, which is the first paper from last year's interspeech. And moving on. There is also work that actually did joint segmentation and tagging. This is again integrating some form of language information into the network. And so one thing that I actually forgot to mention, so for language understanding, there are a few corpora that many people use out there in the literature. One of them is the airline travel information system. The performances are really high these days, so we keep pushing the boundaries of it, but it's shared by everyone. There are going to be a few ones that we will mention later on. But ATAS has been like this place, that this corpus that everyone tries to beat, and then this approach that I'm going to describe next results the highest results currently, although that can change at any moment. So what they do is, in addition, so first of all, they consume all the words, but then they output the segment boundaries. So you can imagine these as like phrase boundaries or slot boundaries, right? And then what happens on the output side is they group the words that belong to a phrase, and then they try to tag them. And these boundaries, you can actually learn this from your training data. So you first do the segmentation, and then do the tagging. And okay, so this is so up until now I have been talking about intent detection and domain detection first. Sure, go ahead, please. So those are the beginning and exactly. You can imagine them as the beginning and inside tags of the previous thing, where the output here would be just the class without the BIO tags. So till now we have been talking about these tasks separately, but there is also work that actually try to jointly model these tasks. And so first one basically says, okay, I can actually see kind of like combining the earlier intent detection work that outputs the intent categories at the very end of the utterance with the LSTM-based slot taggers. So this method would say that actually the frame can be realized as a flat sequence. First you output the tags, and then you output the category of the utterance. In this case, the notation is slightly different. The words are up there, and then the outputs are down there. So it would generate all the word text, slot text, and then it would generate the domain and intent information after all the words in the utterance have been generated. So this work basically included using multi-domain corpora and adding everything into the training data, and has shown significant benefits over just doing these tasks separately or doing these tasks individually in each of these domains. Another study which is along very similar lines, instead of generating the intent, they basically had an extra output for the intent after the whole utterance is specified. So this is by CMU. So, okay, now moving on from joint language understanding, slot filling and tagging, just basically talking about language understanding, but in the context of a dialogue. So this is one utterance just a single utterance. So up until now I've been talking about just single utterances. So in this case we mentioned domain identification. So the domain for an utterance like this is communication. And then intent prediction, in this case it's send email. And slot filling, these are the slots, like there's a contact person, and then there's the subject of the email, etc., etc. So this is just, and then finally these three things are converted to the query to the backend. But imagine this is a single turn, but in dialogue systems not everything happens in a single turn. We don't always get all of the information. Things can happen over multiple turns as well. So for example, the user says send email to Bob, then the system asks like what do you want to put in it? And then the system says, okay, are we going to fish this weekend, right? In this situation, you again do domain detection, intent detection, slot filling, and then try to combine these things over multiple messages. So, the things with dialogue systems is the utterances are usually very ambiguous without their context. So imagine something like Cascal 46. So Cascal is a nice restaurant in Mountain View, but 6 is it's not clear. Is it the number of people, or is it the time that people are looking for the reservation, right? Without context, it's difficult to say. And then you may look at context. So imagine the system said, which restaurant would you like to book a table for and when, right? In this case, it's easy. You can look at the previous system turn and then say, okay, this is the time. I know what it is. But what if the previous system turn is just which restaurant would you like to book a table for, and the person is chipping in the additional information, which happens frequently? Then again, it's ambiguous. But you can look at the previous conversation and say, oh, okay, it's actually for 10 people. Now this 6 down here should be the time. So integrating this type of information in the language understanding has been studied for some time. One of the first studies basically just leveraged the context from each of these tasks as input to each of these tasks, and showed some improvements. More recently, neural team used actually a sequential network. So this is one turn, it's consumed, and then its intent is output. They just did it for dialogue tagging, but you can extend the idea to slot filling or domain detection as well. The hidden layer from the previous turn is input to the next when the next utterance is being processed, and vice versa. So this is one approach. And later on, they actually extended this, because in dialogue there are two sides to the conversation. So there is the user, there is the system. So in their work, basically, they actually separated the user and the system sides, which seemed to help. Other work actually tried to investigate end-to-end memory networks for these tasks. So what does this mean? Imagine a conversation like this, multiple turns, and then we are trying to parse this final user turn. What one can do is we can represent each of these turns with some continuous space representation. And it could be done via anything. It could be a recurrent neural net, a CNN, any network that you want to imagine. Then you can represent the user's utterance, final utterance, in the same exact way, and then try to associate it with the previous turns. So the full architecture is like this. So now you have the history, and then you have the final user turn here again. And then what you are trying to do is, in this case, it's an RNN that learns a representation for the current user utterance, and then other RNN that actually learns a representation for all of the utterances in the dialogue history, in the short-term dialogue history. And what you could do is, this part is called basically sentence encoding. What you could do is you can actually estimate an attention over each of these individual turns to determine which of these turns are more important for parsing the current utterance. And join all of these previous terms with weighted sum, and then combine it with the current utterance, and then input it into the RNN. So this part without the red arrows is the previous RNN or LSTM that I was showing. Now it has an additional input which comes in from the memory. So we have been training these type of networks all together in one hub, and checking what the impact is. By the way, one thing I forgot to mention is you could actually use the same RNN to the current turn and the history, or the same network for both of them. And then multiple teams actually have shown improvements with this type of encoding of memories into the neural network. And one thing that we did is actually basically analyzing what is happening, like what is the system paying attention to. So this is the attention rates over the history turns for this dialogue that we learned, and it's not obviously clear how to present this, but very common trend is in these turns when you don't know what the intention of the user is, the system learns to pay attention to those turns where the intent is specified by the user, so that they can determine if this is a movie time, restaurant time, whatever time it is, right? Another thing that it seems to be paying attention a lot is those confusable intents and where they are specified. So for example, how many is specified up here, and number of people is usually very confusable with what time it is, and then so it pays attention to that part also. So one thing with the previous work is it's basically using cosine similarity to estimate the attention over the memory. Another thing that teams have tried is basically, can we actually learn that attention function? So this work, which is going to be presented at SIGDAL very soon, is basically, these are the memory entries, and there is a feed-forward network that actually tries to estimate the attention to each of these memory entries, estimating yet another memory with the attention this time. And then these are combined at the very end using a bidirectional RNN. At the end of it, the two hidden layers from the beginning and end are input to the user utterances when parsing the user utterances. And this work has shown improvements over the previous one as well. So till this time, both of these works, both of these studies, they are just considering short-term conversation memory. But if you think about it, dialogue, although it's a temporal thing, other things could be important in the dialogue, right? Back-end knowledge, any form of knowledge, or anything that you can encode related to the common sense. Other tasks could also be useful. So one of the studies actually in a very, very similar network, so this is the same again slot tagging network. One of the studies used actually, instead of encoding, or in addition to encoding just the memory utterances, how about we parse the user utterances? So this is our prior knowledge, because we do have parsers or taggers, etc. How about we parse all the utterances, and in the memory, instead of the short-term memory, we have something which is like a longer-term memory, again generated from the utterance. But so the attention over these is estimated in a very similar way, and again the combination of the memory entries are fed into the RNN. So this is basically, the memory now is just guiding the task by integrating in the structure information that's in natural language. And this work tried two things. Imagine, show me the flights from Seattle to Boston, Seattle to San Francisco. Then one can actually use a syntactic tree, like just a parse tree, dependency parse tree. And then in that case, you could use the path from each of these words to the root as the knowledge entries. Another thing to try is basically using the semantic parses of these utterances. So in this case, you could use a semantic parser for abstract meaning representation, and again use the paths from each of these words to the root word. So this work has shown that actually if you use this form of knowledge, even when you use little data, you benefit from this knowledge when you are doing slot tagging or intent detection. It's basically telling you where to pay or what bits to pay attention to, instead of just considering everything in the memory. And one interesting thing that we found is that we analyze where the attention is paid in each case, like with the small data set, medium, large data set. So the attention doesn't seem to change much, and it's basically focusing on those terms that are important for the task and not as much on others. And here in this case, the arrows would show the dependency paths, and then the color encodes how important or how much attention is paid in each of these paths. And as you can see, this doesn't change too much from one data set to another data set. Okay, so at this point, let me very briefly, before wrapping up on language understanding. So in general, you can imagine language understanding is like one of the main components for dialogue systems. So for understanding, but it also impacts how the rest of the components are being learned. So for example, if you're training, for example, an RL agent for dialogue systems, you cannot always just train it with the truth, because in reality when you're interacting with real users, you're going to get their utterances and then you're going to get noisy language understanding output. So this study investigated, is this changing the behavior of the RL agent, and can we actually analyze this type of behavior? So the two groups of curves are basically showing the success rate and average number of turns. So the success rate is like an overall measure for dialogue system. So the higher the success rate is, the better it is. For goal-oriented systems, another measure that has been used is the average number of turns. So unlike the chit-chat systems, I believe this is one of the major differences between those. You don't want the user to keep talking and talking. You just want them to be able to specify what they want very quickly and then achieve success very quickly. So these are two different IR agents, I believe, with DQN, and trained when there is some noisy input. Noise on the input, and then this left curves are for noise in the intent, and then this right one are noise in the slot. And as you can see, they both have an impact on how good the task success rate is at the very end. And the intent doesn't seem to matter as much, but I believe this could also be a shortcoming of the task, because this is a single domain task where there aren't too many intents. So this could change, but the goal is basically to show that language understanding does affect the rest of the training as well. So it's important to do a good job. So for language understanding, it's like one of the most important things is evaluation. So most people use intent accuracy or intent F measure or slot F measure as measures of these individual tasks. Also at the same time, whole frame accuracy is important. So you may ask, why even bother to measure these two things, right? So one cool thing about dialogue systems is even if you make an error on either one of them, you may still be able to continue the conversation and then recover in the follow-up turn. So for example, if you miss a slot, but if you get the intent right, you ask it again and then you get the value from the user. So that's why when we look at it, we usually do this separate analysis in addition to whole frame accuracy. But misses or gaps in the accuracy does not mean that we fail and we won't be able to accomplish the task. Okay, so now moving on to the next task, dialogue manager, and basically specifically dialogue state tracking. Let me just bring some water here. What is dialogue state tracking and what is dialogue management? So what is happening in a dialogue system is, like, the users say things, right? They specify their requests in natural language. And from language understanding, we get a set of observations, or from even ASR, we get a set of observations, the words or the intent or the slots in the user's utterance, right? But what the system sees are these. So it tries to estimate, accumulate over multiple turns what the user's goal really is, and then decides on an action, to do next. So dialogue state tracking is this middle component. What it does is basically giving the user's utterance the previous dialogue state from the estimated dialogue state from the previous turn, and the system's utterance, what the state in the current turn is. So this state information is basically used to do some backup lookup, right? So for example, if the user says, I want to book a table at Cascal, imagine the system gets this is the slot name, then it can look up the backend and then see if actually such a restaurant exists or not. If not, there's no point in asking for the other information. If it exists, then the policy could go and then ask about the values of the other slots for optimum form of interactions. So here are some examples in general, like how what are aims of dialogue state tracking are. So it basically aims to maintain a probability distribution instead of just the one best list. So recover or avoid errors that are coming in from the ASR. So this example is mainly just focusing on the ASR errors. So imagine the user says something, blah, blah, we don't know what they said, but here are the outputs from the ASR, imagine, with their probabilities. So if we were using just the one best, then we would stick to kind. Imagine the user said Android in this case. That's not going to be good, because if we continue with it, then the dialog would fail, right? In the second term, imagine it's still not good. The Android has a lower probability again, but the dialog policy is incorrect in both cases, but the dialog state tracker can actually estimate a higher probability, and then if this thing has been mentioned in 2 turns, then let me boost up its probability and then maintain it as the most probable item in the state. Similarly, imagine the case of language understanding, and then imagine errors or ambiguity in the input. So, for example, the system says, how can I help you? The user says, it's not very readable, but the user says, book a table at Sumiko for 5. Again, it's ambiguous, let's say, so then they have equal probability. Then the system may pick to ask for one of them, right? And then in the next state, actually, it could learn that the number of people, this probability should be boosted because it's not, 5 is not the number of, is not the reservation time. So this could be seen amongst the goals of dialog state tracking. And another thing that we could talk about is actually multi-domain dialog state tracking. So in human-human conversations, or even in human-machine conversations, users do not have a single goal in mind. They actually usually oftentimes have multiple goals in mind. They may be trying to book a table and then see movies afterwards, right? So then one can actually estimate a state over multiple domains, but not a single domain. And in parallel, do the backend calls or API calls in the multiple domains. So if you look at this conversation, so this is a human-human conversation. I chipped it in because the same tasks do apply to analysis of human-human conversations as well, not just human-machine dialogue systems. But imagine the user is, do you want to take Angela to go see movies tonight? And then keeps going on. The first time that's mentioned is 6, but at the very end of the conversation, these would be the states, and then it doesn't have a very high probability, because later on they agree actually to go and then see the movie afterwards. So then the probabilities of each of these items are supposed to change in parallel. And another thing is, these could actually impact their decision, right? For example, if the user says, after the movie, I want to go eat, or before the movie, I want to go eat dinner, then basically if they just specify the movie time, then that also has implications on the restaurant time. But of course, these are all complex versions of dialog state tracking. So the research on for dialog state tracking has been boosted significantly given the dialog state tracking challenges that have been performed for almost 6-7 years now. So the goal here is basically to provide a common corpus to researchers, and then ask them, and then provide them, in some especially in the first cases, provide them language understanding outputs from multiple semantic parsers or language understanding systems, as well as in the first ones also ASR output from multiple systems, and not just ASR one best output, but also ASR lattices or word confusion networks, which encode multiple hypotheses from the ASR systems, and ask them to just compete against each other or against rule-based or very good rule-based baselines for the task of dialog state tracking. So the first one was basically human machine, and this was for the bus information system that was built by the CMU team. And later on, there was the Cambridge restaurant system and Cambridge tourist information. So the two of them are again human machine. This one is has more dialogues and also is more challenging than the bus information, and then this next one is actually multi-domain, and the goal was basically figure out if domain adaptation from one domain to another is possible. The next two ones basically focused on human human-human conversations and dialogue state tracking in human-human conversations. So the first one is focuses just basically starting with human-human and in multi-domain tourist information. The next one is language adaptation. So there is English data and then a parallel Chinese data set. And the goal is to see if we don't have a lot of data in the other language, can we benefit from English data when we are doing dialogue state tracking in the other language. And this year, there is yet another DSTC challenge. The tasks have been announced. There are 3 tasks, and I encourage everyone to go and then check the new DSTC. And moving on. Related to neural network-based approaches for dialogue state tracking, of course you can imagine, just like CLU, there has been a series of studies on dialogue state tracking. So we won't be able to talk about all of them, but just focus on the most common NN-based methods. So the NN-based methods have been widely used, first introduced by the Cambridge University team, Matt Anderson and others. So the goal here is you are given a set of features for determining where the features come from. And then you do have an RNN, right? And then these inputs are, these features are input at each turn. And the goal is to estimate a probability distribution over all the values that this slot can take. So for example, you can imagine something like price range. In the backend database, there's moderate price range, expensive price range, cheap price range. Imagine 3 values only. And the goal is to estimate, given these features and then given this turn, has the price range been specified? Yes or no? Or does the user care about the price range because the value maybe don't care? Or the probability of each of these 3 values given everything? So one thing is these features in this previous work, these features are estimated basically using convolutional neural networks. So on the input side, you do have the utterance, a delexicalized utterance, because the slot values may not necessarily be important at this stage yet. And the lexicalization in this work is done by just matching things in the lexicon, but this is possible only because there is a knowledge base and it only has maybe 100 or 50 entries in it. So it's possible to do matching and then you can easily write some grammars. But you can imagine in a more realistic situation where there are millions, for example, let's take movies, there are already millions of movie names, restaurants, a similar situation, then you can actually use CLU to get an utterance to this delexicalized form. And what they do is they basically train a convolutional neural network. So at the very top of it, so it's 2 layers, 3 layers. At the very top of it is the sentence representation, which is input both for the system turn and the user turn. And Sean actually nicely color-coded this. I'm also benefiting from that. I think it's a very nice figure. And then what happens is, if you know that this, for example, is about, let me read the sentence again, I want Chinese food. So this top network, whatever the slot it is for, so this is about food, what you get as input are those intermediate layers corresponding to the delexicalized slot values as well as the slot names. Their approach also uses the slot names as input features, and then jointly train these 2 networks to estimate the state. So for some time this type of methods has been the top performers in the challenges. And so, as I mentioned earlier, one issue with these type of systems, although they perform really good, is actually the scalability. So, what happens? Like, if you have a million values, are you going to estimate a probability for all of those million values? Plus, on the input side, how do you get those million values? So the next study, which is also very recent from the Cambridge University, tries to tackle this scalability problem. So it's a very similar network, but instead of estimating a probability for all, they just estimate a binary probability for a slot and value pair. So is the price range expensive or not in the given everything, all of the information. So again, the input to the system is the system output, user utterance, and candidate pairs. And so you can imagine representing this as a hierarchical network, where you first try to encode context, then you encode the value, and then check if they are matching each other, if they are matching or not. So, this work is very recent, and they have the highest results on, as far as I know, the dialog state tracking task on the DSTC2 corpus. And so now moving on, I will now give one example from the multilingual dialog state tracking as well. So this work is basically using the more recent data sets, the STC5 data sets that have both English and Chinese data in them. But then the majority of the training is in English. But instead of just using for the purposes of feature extraction. So in the cases of these multi-language data, what you can do is you can just extract features from a single language, right? And then you can actually extract multiple forms of features from the single language. So for example, for Chinese, you can have a character CNN and a word CNN. But at the same time, you can maybe use a translator to get the utterance in English, and then use the representation for the English part as well. So the rest of their network is pretty similar to the previous work, but what they have done is using encoding these three channels using these three channels in the output, in generating the output. So okay. So moving on to dialog state tracking evaluation. So as I mentioned before, there have been challenges that have been used by many sites participated in these challenges. And there are baselines that are rule-based, and then there are participating systems. They're all performing on the same. So what are the measures that are being used? So you can imagine state tracking with respect to the user goal, right? So you can look at the accuracy of the overall state. This is basically like joint goal. You can also imagine computing recall, precision, and F measure over these individual over the individual slots as well. And yeah. So moving on. You want to continue? Okay. So I think at this point we have some time for the break. What we could do is we could just take some questions, and then what we want to do is first group questions, then we move on with the second part, and then take another set of questions. So you want to come up here also? So you guys have any questions? Sure, please go ahead. Yes. So the question was, are there any reinforcement learning methods that apply reinforcement learning to task-oriented systems? And yes, there are. And then we are going to be spending the. We are going to be spending the second half, we are going to be starting the second half. We are actually the reinforcement learning methods on task-oriented systems. Yes, please.
Just a quick question. So it's well known that in reinforcement learning, we've got like a lot of data.
Yes.
What about the newer reinforcement learning systems? How many orders of magnitude more data should we train them robustly?
You do need a lot of data, that is correct, to train them robustly. One of the very common used methods is actually building user simulators to be able to train the reinforcement learning system approaches or dialogue systems as well. And we are going to be talking about user simulators and how to build them in the second part. Yes, please.
Okay. I was just wondering, the idea of the frame and slot, where it's just like there's one frame being represented with many slots. Is there work on or research on thinking about frames as a more complex idea, like nested frames or complex frames? Or,
So I should actually, that's part of misleading from my side. So most of these systems, actually, especially the joint ones, you don't really need to necessarily estimate a distribution or estimate a single frame, especially in the, let me just go back to the slide and then go from that point on. Okay, sorry, I don't, okay, there we are. So you don't necessarily have to have a single frame, especially in this case of multitask learning situations. You can estimate a frame for each of the domains, or you can estimate a probability distribution for each of the frames, and then that's what is most commonly used in the literature. And then the next question is, yes, natural language utterances could be hierarchical or nested, and then how do we capture? So there is a lot of wide literature, especially on corpora like ATIS, where you can actually encode this hierarchical information using hierarchical finite state machines, or even I forgot the approach's name from the Cambridge University, but basically just each state is actually a portion of the tree, and then you estimate the transitions and the slots. In the deep learning work, there hasn't been much, but you can imagine calling each of, so for example, when you are interpreting the user utterances, you can imagine each of these slots being yet another frame, and then inputting it to the network again, and then getting the representations for them.
Thank you.
No problem.
I have a question as well. How do you convert, in the end, the final vector representation into an actual query for the database? Because it's not always an AND. You don't need, for example, AND 5 and 6
Yes.
people and so on. Sometimes it's OR, sometimes it's NOTs, negation and so on. How do you get to the actual query?
So usually what people do, and then this is the case in the I'm just going towards the dialog state tracking. Usually what people do is I'm just going. What people do is take the ones, and then this is the same for the Cambridge University work, this one. You take the ones that have the highest probability, right? But something like that would not actually represent, like, negation would be in there because you can always give something a very low probability, unlike the others. What you could do is, and what people tried, but I don't know any published work, but just past experience, it is possible to actually not just have, like, don't care, but to actually have something that is above this one, that would estimate what the relation should be. And then in addition to that, not in the deep learning literature, but there is some work in the previous conditional random field-based literature where people actually try to estimate what the tag should be in between these values. But these are very important issues that are going to come up with natural language. Thanks. You want to answer one of those?
So my question is, it seems like adding new intents and domains is a bit expensive. It requires defining a new schema. It requires collecting data. Is there any work in the literature of having a generic domain classification, like domain hierarchy, or adding like a methodology to add new domains, cheaper methods to add new domains and new intents to a pre-existing system?
So there is work, absolutely, that are using more generic semantic representations or even like logical forms. The one issue is if you use a generic representation, you still have to need to map it to the language of the backend. So the most common approach has been, why don't we actually use the representation of the backend, because at the end of the day, that's what we are supposed to convert to. But there are systems out there that are actually basically using this form of like generic semantic representations instead of reinventing.
Hi, so you mentioned works about like slot filling and intention classification, but these systems are all trained on a specific domain that has states and intent and actions that's defined by human experts. But what if we have now we've come to a new domain that has very few data and we don't have well-defined request or intention. Is there any work to like automatically to discover this kind of stuff?
Yes, there are multiple studies. Unfortunately, thinking the time will be limited, we didn't mention them. Most common meeting that is used is actually transfer learning. So there is a paper, for example, at this year's ICASP. Let me think about it one second. This year's interspeech, which is basically using just training it in a multi-domain way, training all these networks in a multi-domain way, and basically using definitions of the slots, descriptions of the slots as input features to the network. And things like that seem to boost a lot. When you move on to a new domain, a lot of people have been using, can we actually use some other resources? Like, do we need to train it with the perfectly matching data? For example, there's a lot of work on how to use search logs, click logs for these type of tasks. Yeah, but I mean, the most common thing to try is basically just transfer learning and training it in a multi-domain fashion.
I also want to comment something. For that one, it's also possible there's some way to do this ontology discovery, like based on the conversation. Currently, if we do not have the backend database, we try to learn from the conversation. Like we want to extract what's the concept is more important for this domain conversation, and we extract this concept to construct this ontology so that we can have this backend system and we can interact with we can develop the system based on this ontology.
So you mean that we can build a like knowledge graph online?
Yes.
During the dialogue,
in the beginning, if you do not have any ontology, then you need to learn it from the conversation. Then you assume you already have the conversation between human and human, and you can learn this to construct this ontology so that you can build the dialogue system based on this.
Yeah. Thank you.
Thank you.
Okay. Thanks, everyone. Let's go for a break. At 4.
Hello? Then we need to continue the tutorial. So I'm Vivian again. Then I will continue the part about dialogue policy optimization. I hear a lot of questions about the reinforcement learning, and we will talk about this one here. And also for the recent trend, we also will mention recent work a lot about the reinforcement learning plus the supervised learning for neural dialogue system. Okay. So we know that we want to estimate what the user wants as a dialogue state, but different from the dialogue state, we also need to decide which the system action should be chosen for the system. So this is the dialogue policy. So we want to choose the best optimal action in order to finish the task more efficiently. So this is a dialogue policy optimization. So we can treat the dialogue policy in a reinforcement learning framework. For example, user speaks something, and after the language understanding, go to the dialogue manager, and dialogue manager will select the action to fit into natural language generation and go back to the user. We can treat the user as an environment and the dialogue manager as an agent. Then, based on the observation from the language understanding, the dialogue manager can select action and fit to the natural language generation. So in this framework, we optimize the dialogue policy using the reward signal from the user, because user is our environment. So the goal is try to get the optimal dialogue policy which can select the best action in order to maximize the future reward, like the expected reward. So a correct reward design is very important in the dialogue policy training. So let's think about how can we decide the reward for the reinforcement learning. It's like how can we evaluate the dialogue system. But consider dialogue system as a very special reinforcement learning task, because unlike the game playing, we already have some fixed environment and we can play the game with this environment. for a dialogue system, if we treat the user as an environment, user will involve in this interaction. So they have some human perspective rating as an evaluation of our dialogue. So this is a fully human-in-the-loop framework. So it's pretty difficult because we do not have the fixed environment to do the testing. So how can we rate the system performance? We consider the correctness of the response or the appropriateness and also the information adequacy. Let's think about 3 different types of rating. Like we can get the expert rating, like allow some expert to see this dialogue and try to get the rating from the expert. It can have very higher quality, but it requires higher cost. For another one is we get the user rating. The quality is not good as the expert, but it's okay, and we can save some cost to use only middle cost to get the user feedback. And another one is the lowest cost, which is objective rating. We just use some desired expert and we check whether this desired expert is satisfied or not. And if it's satisfied, we can have the higher reward signal. Otherwise, we have lower one. Then we do not need to hire any people to do this reward rating for us. So they require lowest cost. So usually, this is the reinforcement learning framework for dialogue policy, like language understanding as a observation, and dialogue policy need to select action to do the interaction. We can think about 3 types of different dialogue systems, like the task-oriented and non-task-oriented. The first one is a social chatbot, which is non-task-oriented. It could be formulated as a reinforcement learning framework as well. Like the state is the chatting history, and we want to select action in order to get the natural response. And for the task-oriented, the bottom 2 are the task-oriented dialogue system. And the middle one is infobot, which is to do the information access. For example, we want to know the weather today, or we want to know the schedule of the certain movie, but we do not need to book the movie ticket, we just want to know the schedule. And task completion bot, it need to accomplish certain transaction, like we need to purchase the correct ticket instead of only get the information about this ticket. So the bottom 2 are the task-oriented bot. Like the state are the user current question or the input and the context. And the action is to try to get the correct answer or get the better API calls in order to finish the user's request. So that the reward is very tricky for the social chatbot because we want to engage the user. So usually we want to maximize the number of interactions. But for the task-oriented, we want to shorten the conversation, try to finish the task as soon as possible. So they are 2 different opposite reward signal for non-task-oriented and task-oriented dialogue system. That's why the dialogue development separate into 2 different branches in this research. So our goal is we want to develop a generic deep reinforcement learning algorithm which can learn dialogue policy for all different type of bots. So let's think about the typical reward function is very easy. For example, because we want to finish this task, right? So if this conversation is successful, then we can assign the very large reward at the very end. And also we want to make it as soon as possible, so we just assign -1 for per turn penalty. So in order to maximize the reward, we will try to make the conversation successful and also try to do it as soon as possible. So this is a typical reward function setting. And also, this learning signal requires the domain knowledge. For example, This is very common. We use the simulated user as the environment to do the interaction because we need a lot of conversation to do the reinforcement learning training. And another way is to hire some paid user using crowdsourcing, and we can ask the user to rate this conversation, whether you think this conversation is good or not, and we can use this reward as our reward signal to do the reinforcement learning. And I think it's impossible to directly train our reinforcement learning agent using real user because in the beginning the performance is pretty poor. If we directly interact with the real user, probably everybody will give up in the beginning. Nobody will use your application. So usually before deployment, the user simulator I think it's a better way to choose to do the reinforcement learning based dialogue agent training. So this one is to use the deep Q network, which is a basic deep reinforcement learning model to train the dialogue policy. So given the input is the observation from the understanding, like the semantic friend, and also based on this understanding, we can do the interaction with the database, and we know what's the return information from the database. So based on these two information, this dialogue manager needs to select action in order to interact with the simulated user. And this one can be trained using the simulated user. So you need to have a simulated user which already have a predefined goal, and you use your system to interact with this user so that you can train your reinforcement learning agent based on the simulation conversation. And following tutorial will detail the simulated user more. Okay. And currently there's some issues about reinforcement learning for dialogue manager. First one is the learning speed is very, very slow, and also we have some cold start problem. Like in the beginning, it's very difficult to get successful. So there are some solutions. The first one is we try to use some simple, efficient, actor-created information, like we use the experience replay to boost the performance in the beginning. Let's see this figure, like the solid line shows is the approach with the simple, efficient experiment replay. So you can see the performance will boost quickly in the beginning of the training process. And another way is we can utilize our supervised data, because if we collect some supervised data, we can leverage this one with our simulated user. The one way is we can pre-train the model using supervised learning and then directly put into the current system and use reinforcement learning to do the fine-tuning. So in the beginning, they may have better performance. And another way is we can mix the supervised learning data and reinforcement learning data together during the reinforcement learning training. So we can see the performance can be better using the supervised data. So we can overcome the cold start problem. Okay, so after a deployment, if we interact with a certain user, we want to adapt to the user's behavior, so which is called online training. So we want to learn the slightly adjust the policy based on the real user feedback. So there's several ways. The one way is we want to infer the reward signal from the dialogue. For example, based on this dialogue, we want to build a model which can estimate the current reward for this dialogue, and then use this reward to refine our policy. And another way is we got the user rating directly, and we can adjust the dialogue policy using the user rating. Okay. Also, another another attempt is use the interactive reinforcement learning for the dialogue manager. So here, usually we focus on the final future reward, but if we can have some immediate feedback, for example, in the middle of the conversation, if the user give us some signal about good or not good, we can directly use this signal to penalize our actions in the middle of the conversation. And also, I'm not sure whether this is too small to see, but you can see that here the user say, "Oh no, stupid." The user shows some frustration. Like if we can detect this negative feedback, we can directly use this information into our intermediate feedback and to refine our dialogue policy. So the idea is we want to build a third agent which can provide interactive feedback to the dialogue manager. So which is a little like the reward shaping and the policy shaping. For example, in the beginning, we focus on maximizing the information for the final reward. But if we have the intermediate feedback, we can maximize the information here so that we can have better performance. So for dialogue management, evaluation is pretty tricky because we can evaluate for each turn or we can evaluate per dialogue. Okay. So for turn level evaluation, usually it's focused on the supervised learning, so we can estimate the current turn, whether the current turn is correct estimation or not. So we can measure the system action accuracy, and also for the dialogue level, we usually compute the task success rate for the task-oriented dialogue system. And also we can also see the reward signal, because if we have the higher success rate, but if we can make it as soon as possible, we can have higher reward. So there's two different approaches for supervised and for the reinforcement learning, respectively. Okay, so move on to the next component, which is the natural language generation. For natural language generation, the idea is we want to mapping the semantic frame into natural language. Like if we design the current system action is to inform the name is equal to 7 days and the food type is equal to Chinese. We want to, the NLG component need to convert into a natural language, like 7 days is a nice Chinese restaurant. So you can think about very simple approach like template based. We can have some expert to design the rule to map frames to the natural language. Like if you want to confirm something, you can use this pattern, and you want to confirm the certain slot, you can use that pattern. This way, the process, which is very simple and error-free and easy to control. You don't want to say something is unreasonable or ungrammatical. In this way, you can control all information you output. But the cons is it's pretty time-consuming, and it's difficult to have large scalability. Because if you have another domain, you need to design a whole mapping for different frame and different natural language. So the next one is try to use the plan-based NLG. Here we separate the problem into a pipeline system. Like this is the input, like we want to inform something. And the first one, we construct a sentence plan generator. They generate several different sentences using syntactic tree. And we want to select top one syntactic tree as the best sentence, and then we do the surface realization to fill in the value for each slot. Then we can have the final sentence. So each component can be implemented using a statistical method, like statistical sentence planning generator or the surface realization. The pros includes it can model very complex linguistic structure because we have the syntactic tree in the middle. But the concept is very highly engineering and also require the domain knowledge. So it's not ideal for the large scalability domain. So this one is first attempt to use the language model to do the NLG. The idea is use the class-based language model, which the idea is pretty simple. Based on each class, like what we can train the language model, and we can during the decoding, we can decode each word based on the given information, like given class, so that we can decode the corresponding sentence regarding to this given information. So this is a framework. So for the dialog manager, they want to select these actions. So how to do the generation? First, they generate several candidates here and do the scoring. They just select the best sentence here and do the slot filling for the sentence, so they can accomplish the natural language and do the text-to-speech and go back to the user. So it's very easy to implement and also simple and easy to understand, but it's computationally efficient. So another ultimate way is try to build some network. This one, which based on the information in the from the dialog manager, we build a semantic dynamic belief network and also the phrase dynamic belief network, and to train it together and try to map the original concept into the phrase and accomplish the whole sentence in this way. But here, they require the alignment between the original concept and the phrase, so that they can train it together using these two different networks. So the process is very efficient and the performance is pretty good, but it requires the semantic alignment. It's not easy to get. For some small domain, it probably not too difficult, but for if we have multiple domain, it's a little difficult to acquire the aligned data. So I think this one is the first attempt using the RNN to do the natural language generation. So given the input is the semantic representation, want to inform the name, the restaurant name, and the food type. And output we want to generate like the name serve this food. And so we need to do the delexicalization first, so that we can allow the different value for the same slot has the same weight, so that because the slot value is not important, but slot itself is important for this generation. So this is the RNN module to do the generation decoding, and we want this network condition on this dialog act. So we map the original dialog act into a one-hot representation. For example, here means if they have the inform or request, like one means they have this information, and the following dimension means the different slot. If they have this slot need to be informed, they will have the 1, otherwise they have 0. So that this one-hot representation means the dialog act corresponding to the original input. So given this vector, and we can train this NLG using the end-to-end neural net. But they have some problem because they always condition on the same vector. So the issue is they will repeat the semantics several times. For example, Din Tai Fung is a great Taiwanese restaurant, they serve Taiwanese. Or Din Tai Fung is a child-friendly restaurant and also allows kids. But we do not want this. It's not ungrammatical, but it's not natural for the response. So we want to control the semantic information. So they have different ways to solve this problem. Like gating mechanism and attention mechanism are the most popular ones. And I will describe this one using the gating mechanism. This one I think is the standard way to do the current dialog system NLG model. So this is the LSTM. And we know that there's a LSTM cell between the whole network. And they invented another dialog act cell, which means this is the original dialog act representation, 100 representation, as I mentioned before. And they want to, after they generate a word, they want to update this dialog act representation word by word. For example, assume you already mentioned the food about Chinese. You already generate the word about which is Chinese. Then we hope this dialog act cell can update this value from 1 to 0, so that in the following word they will not generate the repeated semantics again. So the whole network can be trained together, and they would automatically decide which information they need to get and which information they need to update. So this idea is using gating mechanism in order to control the generate semantics, so to avoid the repeated semantics. Okay, so here there's a very interesting work recently that this is considered structured information for NLG. Like this is the information we want to generate, and they use the syntax tree to do the generation. And how can we encode this syntax tree? The way is very intuitive. They just encode the whole tree as a sequence. They flag the whole tree and use the sequence-to-sequence model to do the generation, so that you can do the conditional NLG using syntactic information. But it requires the syntax information for the original sentence, original semantics. And another way is the contextual NLG, which is also similar to the NLU. So this is the typical NLG. If we want to inform the bus information here, I think the standard way is like take bus, blah, 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 and this is the not bad response. But if we consider the context, like previous term, the user asked, is there any option? And I think the better response is, oh, there's another action, which is blah, 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 like this way. So this one is more context-aware response. I think the original one is also correct, but the context-aware one is better. So it's more natural and for the human perspective. So the goal is try to adapt the user way of speaking, try to provide the context-aware response. So the model is pretty easy. Like they also use the sequence model to encode the context and also do the decoding for the final context-aware response. And the recent work, which is very interesting, using the new generative adversary network, which is GAN framework, to do the natural language generation. Like they have a target sentence attribute C in the middle, so we want to do the language generation, and another discrimination will try to see whether the generated sentence is natural or not, and also check whether the target information is mentioned or not, in order to do the whole network training. So the encoder and generator and discriminator will be trained in the end-to-end manner iteratively. So this is a latest one. I think it's very interesting. So that's I think NLG evaluation is very difficult because we do not have it is an open question until now. We do not have a good solution for the natural language generation evaluation. Like the metrics we used for the subjective, I think the human judgment is good because human can say whether the response is good, like fluency or the adequacy or the readability or the variation of the sentence. But it's very difficult to get the subjective evaluation for the research community. So usually a lot of people use some objective metric like the Broad score or the Roach, or compare the word embedding overlap, like because we want to mention this semantics and whether we mention the same semantic or similar semantics in the response. And there's also some work shows that currently there's a gap between the human perspective and also for the automatic metrics. So we do not have an answer about the good natural language generation evaluation. So usually we need to get the automatic metrics first and do some real user study to convince the people this response is not bad. Okay. So for the following tutorial, Asli will take over the rest.
Hi. I hope everyone is, not everyone is sleeping, I can see your eyes. I'm going to be talking about evaluation, and there was a few questions during the break about how to train reinforcement learning based dialogue systems, and we're going to be talking a little bit about those and some recent, very fresh, which came out like a few weeks ago kind of papers. There are really good applications for, variations of different applications of dialogue systems. So I'm going to start with the evaluation first. So we've talked about evaluation of each of those components for NLU, dialogue state tracker, dialogue modeling. So I'd like to take a look back a little bit and look at it from a bird's eye viewpoint of how, given a dialogue, you would measure it as a success. And there are a few ways that the research community have approached this problem, and in both of the types of dialogue systems, one of which is the task-oriented or chit-chat. The first one, you would probably see more the dialogue model evaluation using crowdsourcing or user simulator for task-oriented dialogue systems. The second one, the response generator evaluation, is mainly seen in chit-chat environments, but both can apply to both dialogue systems. So I just want to mention a little bit about how one would evaluate their system. So assume that you have a fantastic dialogue manager and you want to evaluate your how good is your model. And one way is to just ask the crowd. In this paper, for instance, and we've seen in other papers as well, the users are asked questions about either agent to human or simulated agent to a dialogue manager agent conversation, and they're asked to judge it based on how confident they are in judging the dialogue, or if this task has been fulfilled. This is mainly for the task-oriented dialogue models, and if there's a really good flow and it's if the dialogue has been completed fully, and how is the user's overall impression? So I'm just giving you examples. There may be many others, but these are the kind of things that might be subjective, and you may want to use them in either training your original dialogue manager or retraining it. Perhaps use it as a reward function. So there's also a bunch of other things, and people have been looking at some statistics based on these dialogue outputs that they have generated with their maybe cold start model. We've been talking about user simulators, and Dilek and Vivian have mentioned a little bit about them. So user simulators are mainly models which can enable your reinforcement learning-based dialogue manager to explore, a larger space, or to be able to actually train. It's because dialogue systems, reinforcement learning systems, are interactive, and you need another agent or a human. And as Vivian was mentioning, it's really not one inexpensive, or maybe your dialogue system is actually not very good, so you may not want to show it to the users. So you probably want to use another model that will act as a user. So that's why the user simulator comes from. And third, collecting and annotating this kind of a data, human-to-human conversations or human-to-machine conversations is actually really costly. So you may want to use some sort of maybe a expert system-based or a rule-based kind of a system to build this kind of another agent that helps you to train you. So it's like a chicken egg problem. You want to build your reinforcement learning agent, and you build another agent to train your other agent, but still these work well. You can think I also use this analogy, especially for instance, on top of my head, OpenAI actually has this GYM framework where you train your reinforcement learning agent and you need an environment to get the reward or to just run it against. You can think of the user simulator as your environment. So I actually said most of the things that I want to say in the slide, but I'm going to go on anyway. So, the user simulator interacts with the dialogue manager, and so we're going to be talking about in a few slides how we build these user simulators. It's basically looking at the real user conversations, or what the real user might have said in certain constraints given a domain. For instance, if it's a domain-specific dialogue model. So there's this bunch of steps that you need to follow in order to build your user simulator. So the simulator keeps, for instance, a list of goals. As you can see from the top, I'm just listing a few things that you need to follow, and a bunch of actions that it needs to fill out. You can think of it as like an agenda. A human has an agenda in a task-oriented dialogue system. User simulator has the same agenda. It starts with, for instance, if you want to reserve, assume that we keep saying, I want to give a very simple example, reserve a seat for 2 in Cascal, for instance. You would first want to ask for, the time that if the 2-seat table is available and comes out, follows different constraints. The user simulator knows about these constraints, and while conversing with the system or the agent or the dialogue manager, tries to feel which of those constraints have been replied back correctly, and then moves on to the next constraint until all the constraints, which constraints meaning the agenda that he has, are fulfilled, and then it just gives a reward at the end. So there are different ways of giving rewards to the dialogue manager, one of which is just you don't give any reward, you just give it at the very end, or very standard reinforcement learning algorithm where you just discounted reward -1 is each step, or you may have your own reward function where there's a really good constraint, the very important constraint that you really want it to be fulfilled, then you could have a different kind of a reward function for that. So user sim, as you can imagine, this is kind of, it has this kind of a model, which is actually my next slide, that either be built using a rule-based system, or I'm going to be talking about in a few slides, they could be learned using either from data, labeled or unlabeled. So assume that you have your dialogue manager. You just think that it's okay, and you want to really train it using real data set, and you don't have actually data. You don't have any data set from restaurant domain that you want to build your conversational agent to fulfill a task. So what you do is you use a user simulator which has this user model which I talked about. It knows some constraints. It could be either rule-based. You could just say, okay, this user simulator should the first thing it asks is the location of the restaurant that they're looking for. Maybe it's a Chinese or Taiwanese restaurant, for instance, or maybe the time is important for the user. So you just sort of build your simulator based on what you would expect your system how your system should react. So the user model first, for instance, starts with if it's a rule-based, usually it starts with a template-based approach. For instance, it asks for a location or the time of whatever the object or entity you're interested in. However, in a real conversations, the utterances are in natural language, and there is usually a noise in either the ASR engine or maybe the language model or even your spoken language understanding model. So we would like to introduce this kind of an error. For instance, we just add, delete, or any standard kind of an error that you could introduce might help. We usually, in this kind of setting, we usually introduce a language understanding error so that the downstream, which is the dialogue state tracker and the dialogue modeling, can actually handle, or it's because it's trained interactively, it is more robust to these kind of errors because it's going to get the reward, which we're going to see next. So now we have this kind of a template-based information, maybe the location, requesting a location from the system. So we want to ask, like in Mountain View, for instance. And the dialogue state tracker just fills that slot, and then the dialogue policy actually gets that state representation wherever time step you're in that dialogue. Spits out a dialogue act. In dialogue systems, usually the output of a dialogue manager or dialogue policy is discrete, especially for the task-oriented dialogue systems. It's not like the games where the output of a policy is a continuous function. It's usually, we get a distribution over the number of the actions that that your system is supposed to handle. And then user model is actually sees this act, and then what it does is just goes back, okay, so what I was looking for is a restaurant in Mountain View, and the system goes back and checks with this doesn't work. Here, this is the back end. So the system actually, before getting the predicting what the action it's going to have, it just goes back to the database or the knowledge base and gets the information and just says to the user simulator, hey, okay, yeah, there is a restaurant available. User model now knows that this constraint is fulfilled, uses its reward model, and sends back the reward to the dialogue policy, which is a reinforcement learning agent, if you recall. So this is the way how we train the dialogue managers if we don't have any data available. Dilek and Vivian and we three of us actually, we've been involved with this rule-based simulator in one way or another. There's actually an online user simulator for a dialogue, for building a dialogue manager. If you are interested, you can just go and download this tool. It's on GitHub. It is a rule-based simulator with a collected data set. It's on one domain, one single domain, which is a movie booking domain. And what it does is actually very simple, but gives you an idea of how you would build a system using a user simulator. And then you can use this framework and build your own simulators depending on what kind of a model domain you have. Or you could use a multi-domain system if you like. This is available online. You can download it, as I mentioned. Aside from rule-based user simulators, there's also model-based user simulators. I'm just going to list them a little bit quickly here. The Biogram models have been used quite a while ago. Actually, I say quite a while ago because like last year's papers are old now, so 2016 will be really old. Biogram models didn't actually help for the variability in language understanding. That's why especially statistical models, people have switched to building statistical systems for user simulators. And they started with, for instance, graph-based models where the arcs were the actions and the nodes were the choices that the system could take. Then, more recently, data-driven simulators, which I'm going to talk a little bit about, and neural models, which is the main goal of this tutorial also, have emerged for building user simulators as well. So let's talk about the data-driven simulators a little bit. So it has very similar to the rule-based, but these folks have actually introduced a few different models to train their user simulator. What they did is they have this user intention simulator. They do take the current discourse status and previous user current semantic frame, and they train a CRF kind of a sequence model to predict in a semantic frame kind of a request for the user. So, like for instance, if the utterance of a user would be, I want to go to City Hall, the request plus search log would be requesting the place, and the search location is the City Hall. So with this kind of a sequence learning algorithm, you actually predict what the user would have said in a template base, and then the template is converted into natural language utterance using this utterance simulator. So what it does is it uses, like for instance, request plus search log is converted into I want to go to the City Hall, just to mimic how a human user would have said this kind of, if their request was such. And they use a bunch of part of speech tagging rules, combined with language modeling to come up with this user utterance. And also they add some ASR errors just for the robustness of their build system. And they do sort of send this to their user simulator, and then this interaction continues. During this interaction, they collect a bunch of data, show it to the user, measure it with the blue or rouge or what have you measures that we have mentioned to measure how their dialogue system is doing during learning. And then they go back and fix their models based on that. More recently, last year I suppose, neural models which use sequence-to-sequence have been introduced for building user simulators. Actually, this study is more like extrinsic reward shaping model. What it does is it actually uses labeled dialogues so each of these C's, you can think of them as like each turn in a given dialogue, and it could be user's turn, system's turn, user's turn, system. But these are actually more interested in what the user's action, I believe, is. So they just built this sequence-to-sequence model where the output is actually sequences of actions, and they do use this for extrinsic evaluation for their policy. Very interestingly, following that, this year, Interspeech, I think, there's another work which does not use any labeled data, only use natural language input, natural language output kind of a model. They train this sequence-to-sequence. They collect this data from human-to-human conversations and build their user simulator from that human-to-human conversations. So this model requires a lot of data, even to train a user simulator. So we started with the rule-based, which required no data. Now we're going to more data. So there's sort of a trend because there's a lot of data set out there. So I suppose that, combination of the rule-based with the data, you would probably be building a better user simulator, in my opinion. So as I wrap up for this part, the user simulator part, so it's important to understand how your dialogue model is doing. User simulators can help you to do that, and because like you can measure the agreement between the user and the system, not by just looking at the blue or this kind of metrics, but by just using some subjective or maybe the objective. It just depends on how users react, decisions, and use the actual human who is going to be the end user of your system that you're actually building. So it's much better to use this kind of evaluation metrics than building a human-to-computer interaction models. With user simulators, you can actually measure the efficiency of your dialogue manager by just looking at the number of the dialogue turns. If you want your system to finish in 10 turns, and it's not okay to finish it in 15 turns, then you just give it a very bad reward, then your system learns to finish it really quickly. So there's like different ways of using your simulator to your advantage. Also, you can look at the ratio of your dialogue turns. Now you're probably getting the idea of using this user simulator to shape your reward, for instance. And also, user simulator can be used to measure how the system reacts. For instance, system might just not understand what the user have said, might just ask, did you mean this? Or, just say, okay, I have this available, meaning that I didn't understand this, but maybe you're asking this. So that user simulator can just confirm and just measure that, oh, okay, I filled this slot, so I'm going to give you a good reward, kind of a way. Okay, so this sort of wraps up how you would use a user. Oh, okay, yeah.
Do you have any metrics for the user simulator? Do you know how good they are?
Yes, we do. We have number of turns, for instance, or the success rates. Success rate could be a combination of different measures. Like I said, number of the turns. I can't recall any. But it is not just one single measure that compares, golden to what is predicted. It's more like how a user would be satisfied at the end of the dialogue, kind of a way. If all the slot constraints are satisfied, is what I can think of. You guys can think of anything else for the success rate? Yes. I think we mentioned that too.
Say you have a user simulator and you work for another week. How do you know that it's better?
Is better? I suppose you'd probably be getting, you could actually we have shown some graphs, right? You do train your system for multiple turns, and then you get you measure your success at every end of dialogue. For instance, you just measure it for every 100 dialogues and get a success rate. Success rate would be, like I said, a combination of finishing it in 10 turns, and if it's like over 10 turns or however turn you want, then you just don't get a really good reward. So if the new policy that you've trained gives a better, a higher curve than your previous curve, meaning your success is better, then you might also say, okay, I'm very satisfied. I mean, there might be others that you want to add, I guess. Yeah. Yeah. We'll probably did we put that? Maybe we can put that at the very end. Thank you, Dilek. I hope it answers the question. Okay. So I'm going to actually interest you with this paper, which I find really interesting, how not to evaluate your dialogue systems. These researchers looked at a bunch of different measures, and like blue or meteor or embedding measures, and they found out that these measures, automatically evaluating these kind of measures, the quality of the dialogue systems is a challenging problem. So existing these methods like this metrics are actually does not really correlate with the human responses. For instance, if you look at on the right, the model response actually doesn't have any word overlap with what the reference response is. But that will give you a very bad measure if you use a word overlap, for instance. So these folks have actually, in this paper, they have shown, they have built a system. So they collect a bunch of data. They built this evaluation system that learns to predict human-like scores to input responses using a new data set based on human response scores. And so they do train it on this data set, and they show that their model predictions correlate really well with the human evaluations. So it's very interesting. I like to suggest this paper. I mean, I haven't tried it, but it might be interesting to look at. So they have found that this even it generalizes to other domains as well, is something that is interesting in this paper, in this work. So I want to switch to a little bit of the recent trends and challenges that we faced for building these dialogue systems. And one of the things that have been for the last 2 years is, especially for the chit-chat, like non-goal oriented dialogue systems, but we have been seeing a bunch of these hierarchical sequence-to-sequence models, which are comprised of multiple different RNNs. For instance, the encoder here on the left. So here, the encoder is an RNN. It decodes the user utterance into a vector, which is actually sent to another RNN, which keeps track of the context of the dialogue. And its goal is to send this information that it collects from the current utterance and the previous history, and it starts to generate, and sends it to the decoder to generate the next system response. These kind of systems work very well. I mean, I shouldn't say very well, work okay for chit-chat type, very simple domains. However, they have problems, as you might imagine, coming from the constraints of the sequence-to-sequence model. For instance, they tend to generate shorter utterances. They tend to generate generic responses. So they don't use, although they do look at the context, still they, because it's the maximum likelihood model, still you don't get actually the feeling that a human would reply. So what they do, there's another very recent work by these researchers. What they do is they just actually introduce a latent variable, which is a constraint to their model. What they do is, with this latent variable, is they constrain the semantic space. So when you given a user utterance, the system, when you generate the system response, it is actually dependent on this constraint that whatever you are generating is not that generic, but is specific to this latent variable. You can think of that as a topic or like a sentiment or whatever context you are given that window of that dialogue. These kind of dialogues tend to be longer, so it's very important that you capture the context information while you're training this kind of a system response generator. There's a very recent work by researchers that have looked at knowledge-grounded neural conversational models. So they looked at this kind of, so I'm showing you an example. It's a social network space, and user is just like talking to an agent, and it says, going to this, I can't see, whatever, X restaurant. And the system is, needs to reply with some contextual information, like for instance, the human would have said, "You'll love it. Try omasake, the best in town." But what the model generates is very generic, the same response that we get from the sequence-to-sequence model. Have a great time. But there are a lot of information on the social networks where neural networks models can actually use to either as a constraint or a feature, what have you, as a factual information and ground the conversation based on these entities that they see within these social network conversations, which is shown on at the top. So here are some examples that you would see in this kind of a social network environment. So this paper actually utilized those while doing the sequence-to-sequence model. What they did is they present this fully data-driven approach to sequence-to-sequence model, and rather, so they have a decoder, so they have a few steps. So they have a decoder up here, this one, but then they also use contextually relevant facts, and then they encode that as well. Sorry, this is an encoder. So they have an encoder. So given an utterance like this, so there's a context, like the user is saying that they're going to a restaurant, and it's very specific, it's a Japanese restaurant. And then they do collect a lot of information about this type of a restaurant from the social media, and then they also append this information together with whatever they have decoded to decode the system response. With this way, with grounding using the facts, the external facts, they do generate more versatile and robust and context-aware system response generator. So I'd like to talk about a little bit of, which actually we did talk about them a little bit, end-to-end joint learning approaches. But it's these are more recent ones that have been tried. The researchers here looked at how, so you assume that you are training your dialogue model, but you don't know how your dialogue model affects your natural language understanding. So they looked at how these errors of the dialogue model would backpropagate to your NLU component, and if actually doing this would affect your NLU as well. So they did evaluate their semantic frame accuracy, and they showed that if you do train an NLU model together with the dialogue model, and Dilek was mentioning earlier that the joint model is actually producing better in this kind of task-oriented environments, you would get a better performance for NLU as well. This is saying what I was just saying before. There's also very so I'm going to be showing very recent but very similar work, which are sort of trying to build these dialogues end to end. And there's a from last year, there's this work which looked at each of these components. For instance, the intent network, which parses the utterance using an RNN kind of a model. Generates a distributional representation, and also they have this belief tracker which takes this utterance and tries to build for each type of slot in their semantic frame a distribution of over the values, which is like a probability distribution of what the value of the slot type it would be, because they are template based. And then given the maximum, the winning slot and its value, come up with some sort of a query, like an SQL query. Is it here, as you're seeing? Do a search in the database, come up with a vector, as you're seeing in the red here. And they do use all this information, the RNN encoder, the belief tracker output, and the response they got from the knowledge base, to send it over to another very simple DNN network, which they call the policy network, and it outputs a representation, and you would assume that this is really representation over actions, which gives an information to the sequence generator for the system. So the user says, can I have vfood, that's the delexicalized form, and the system generates vname serves great vfood. So it's just, you learn to generate a system response given all this component-based information which are trained end-to-end. And then they do, in their paper, show that if they do use the information from the database and replace the delexicalized forms, they automatically have the system response generator. This was from the Cambridge, I think, work. Dilek mentioned this a little bit before, how memory networks can help to build, especially natural language understanding models. Folks at FAIR actually used this, one of the DSTC data set and converted it into a way that their memory networks can work. If you read the paper, which I'm showing a link to, their goal is not to build a fantastic dialogue manager or to be able to understand anything. What they wanted to do is to show that memory networks can help for tasks like not to finding where Mary put the apple is, but also how you can do API calls, or how to update like if the dialogue model requires that you need to update an API call, or if there are if a lot of options that are returned from the system, can the system be able to pick the one that has the highest probability and generate the best system response out of that? So they, and also some of the other things that they looked at, they were their performances actually worked well on some of the simplest tasks for the system response, but not well for the real scenarios, which is like the last row that you're seeing on the left table, which is actually the real dialogues. So this kind of a work, in my opinion, more like a supervised approach. It doesn't have this interaction which we usually see in a dialogue modeling, but these are a different kind of approach to dialogue modeling, I feel like. We didn't talk about this dialogue database perspective. It's actually very important for building this dialogue manager and replying back to user or getting back to user the right information. It's important that the system knows what to search in the database. And these folks in this paper have looked at that problem. So they looked at this multi-turn dialogue agent, which helps, which helps the user search for knowledge bases without constructing a very complex query. Let's assume that the user, in her mind, wants to search for a Bill Murray movie released in 1992, and rather than generating this very complex sentence, it just starts with a simple one. It just says, find me a Bill Murray movie, and then the systems asks, so let's look at the dialogue first. When was it released? So it wants to come up with an answer by just asking another question. So they converted this knowledge or sort of a question answering problem by using a dialogue modeling that we have been seeing throughout this tutorial. So so user says something, the belief tracker you can think of this like an SLU. It just parses the utterance and comes up with a semantic frame of the utterance, sends it to this knowledge-based lookup engine. So this is what the main goal of this work. Actually, what they do is they come up during the learning stage of the dialogue. Every turn, they do come up with statistics, like the probabilistic measure of each of the entities that they define in their knowledge base. To complete this flow, so that if you can think of the dialogue, hard search in a dialogue returns discrete values which you cannot backpropagate towards. But with this soft knowledge base, where these authors actually define a probabilistic value to each of the possible slot value pairs, they could just backpropagate their policy network back to the user, which actually makes this model really robust. And they do, so this is what is this paper about. And the red one that you're seeing actually beating all the other ones, this is one of the ways that you would measure your dialogue model by just looking at your success rate during testing time. There's another one. There's quite a lot of work with this end-to-end learning approaches, and this approach looks at end-to-end reinforcement learning-based system, where they do learn NLU, state tracker, and dialogue policy together using deep neural networks, and they do train their models, reinforcement learning model using a deep reinforcement learning. One thing that they looked at, which is the core core of this paper, in my opinion, because we have been seeing these kind of models before. They looked at an RNN-based kind of a policy network, which uses the context given a window as information while trying to predict what the next action is going to be using a Q network. I think in this work. And then they do suggest that this kind of context information and building a system, training a system together for understanding, tracking, and policy learning is actually much better than training them individually. There's another work which might be interesting for practitioners, which simplifies this dialogue model and looks at it in a way. It's actually very practical because it uses an LSTM based of a model of a dialogue policy learner. It can map from natural language utterances to system actions, not by just looking at the raw utterances, but also system developers and engineers can actually provide information to this type of a system, like additional features or some constraints, so that the LSTM learner, which could be a supervisor in reinforcement learning base, can continue this interaction, predict what the next action is, and go back to the user and generate an utterance. So they have like multiple different components based like entity tracker, some other API calls that we have looked at before, and they also suggest they use the same data set that the FAIR people have used, and they show really good improvements because they have been using an interactive system. But it wasn't the goal for the original paper anyways. This kind of work which we have been talking about, this work combines all of the components that you would see in a dialogue system that is trained with a human without a human information existing. So it has a user simulator, which has this user agenda modeling, which starts with a rule base, but it has this NLG component in it, which converges into a natural language utterance with some noise, so it's very natural for the language understanding to receive a sentence with some errors. The natural language component is trained for each multiple domains, which knows how to map the natural language utterance into semantic frame, sends it into dialogue manager, which spits out an action with some probability, sends it to the user to expect some reward. This approach is actually can be trained supervised or reinforcement learning based, and the researchers here used all of the rest of the components except the dialogue manager is supervised. The dialogue manager is trained with Q networks in the system, and they do show that the important part of this work is that this kind of a training algorithm, which uses user simulator is partially model, partially rule-based. You're seeing the rule-based system on the left and the reinforcement learning system on the right. They compare it with the rule-based policy learner. What they have seen with this kind of a user simulators is that they do first not repeat itself, doesn't actually ask the same slots or constraints. So the reinforcement learning system knows how to follow which constraints have been fulfilled, and some other silly mistakes we don't see it, and because we're using this learning and reward function throughout the system, the dialogue, the length of the dialogues are shorter because you're rewarded for the number of the turns that you have in your dialogue. So the system can learn how efficiently interact with the user if you use all these components back to back and train them together using their errors, back propagating to the down to the language understanding part. Sorry. There's a very recent work that looks at hierarchical or for hierarchical reinforcement learning for composite tasks. Dilek has mentioned about using complex structures like travel planning and some other methods. So these folks have actually looked at how you would build not a single domain but multiple domain scenario where there are constraints that affect the other domain. For instance, in a travel planning, you book a hotel, but you have, as a human, while you're booking a hotel, you have the flight in mind. You don't want to book a hotel before you land to a place, right? So you want your agent to be aware of these kind of components, so you can build a multi-domain system or like a composite way, composite model, composite reinforcement learning model that will learn this kind of an interaction. So I'm sure, like for instance, number of the flights should be equal to the number of the people checking in a hotel could be one constraint. And you want your model to be aware of these constraints. If not, ask the user if these constraints should be fulfilled. And these folks have built this kind of a system using two-level reinforcement learning model that are trained simultaneously. One of the the first one was a meta controller, detects which of the domain it should first try to ask the user about. Like for instance, it may start with a hotel, and then, so that's the first goal here. The first agent, the policy learner just says, okay, I'm going to ask the user about the hotel. And then it goes into the second one, which is the controller agent. It just converses the user by asking questions about the hotel. And then when those hotel constraints are satisfied, which is determined by the user simulator, also a complex, like composite-based user simulator, it goes back to the meta controller, so gives the controller back. This meta controller, now knowing that the hotel has fulfilled, maybe not fulfilled, goes back either to the hotel or the next domain. Maybe it's the flight one to continue. And the user might actually, during this one, might change the flight return time so that the system knows to go back to the hotel, ask the user, hey, you want to just also change your hotel reservation? Kind of an interaction is possible with this kind of a hierarchical reinforcement learner. Okay. So from that on, I don't know how we're doing with time, but I want to talk a little bit about 15 minutes? Okay, I'll just go quickly. These are, I'm going to show you a few applications of how dialogue systems have been used, or what kind of inputs have been introduced to either an LU or any component that you've seen throughout this tutorial. So for instance, these folks here integrate neural signals into their dialogue system so that they can recover from ASR errors or language modeling errors or any kind of errors that you might see throughout up until your language understanding component. I'm moving on really quickly. There's another work that have actually used information. So assume that you're in your living room and you just say, I want to see a movie on TV. And you have your Kinect or some other device actually sees the environment and replies you back with saying, oh, okay, so you want to turn on, turn on your TV. Just say, oh, may I turn the TV on or something. So there's clues from an environment or an image or any kind of interaction with the human, it could be pointing, can help predict a better intent for the user's utterance, or any of the downstream dialogue modeling tasks also. There's also some research that looked at, I'm going to quickly talk about this, some app behavior. For instance, when, so you're using your phones and you just say, okay, send to Vivian. Send to Vivian might be an email or a message, or it might be using I don't know, maybe Google Now app, or some other Outlook app, or any kind of app that you have used before. So personalization in dialogue models, or the way you use your devices, actually has an effect on how the system can perceive or help to uncover or the uncertainties that like an utterance like this, sent to Vivian, might have. So there is some studies that are looking these kind of behavioral or usage information and combining it as a context information for their language understanding models. There's actually very interesting work that came out, I suppose, this week. There's a new data set that looks at video highlight prediction. What this data set does is, it's actually very interesting. They look at this League of Legends game. So it's a two-player game, but then when people play this game, there are also people watching those people playing that game, and they do converse. So there's this dialogue happening while those people are playing a game. So there's a bunch of inputs here. There's video input, there's text input. You might have seen this on your phone while you're using this Facebook app, for instance. There's a video, one guy is like doing skiing or what have you, and people are commenting and saying, okay, how cool is it, and all that. So they've collected this data, and they annotated it, and the goal for their case is to just find out the highlights of that video. So it's actually important that you just provide, especially for those gaming events, provide some highlights while you're watching the game, rather than reading all what those people are saying. So this kind of a data, actually, it's multimodal, multilingual. It's very interesting, and I feel like this might be open up some other research areas. In this case, it's very simple. We just want to highlight, but there might be some other interesting research here that we might see soon. So we've been talking about the dialogue breadth throughout this. We've actually talked a lot about this during this talk. We looked at the single domain systems. We looked at extended systems, how we can use transfer learning. We looked at multi-domain systems, how those can be trained, composite tasks and all that, and also open domain systems, which go to more like a chit-chat environments. I don't really have time to go over all this work, but this is very interesting work, and I think there was a question here before about like if there is a new domain, how those previous domain actions or intents can be used. This is an example to that, and if you're interested, you should go and read this paper. What it does is, it's actually one-shot learning. So what it does is it learns a relationship between the utterances given an intent. It's a constraint relationship, a constraint model, which learned representations in terms of embeddings of each of those utterances. And if you do have a new intent that might look like what you have seen before, using this kind of a model can help you to cold start your building a new natural language understanding models, for instance. They have shown that this kind of a model can also help you discover new intents for building a new spoken dialogue system. I think I'm gonna pass this one. All these work, the last few slides are showing domain adaptation and how these models are being trained. And this is actually, you hear a lot of NLP people, you have seen frustratingly easy domain adaptation by Haldome. So the folks here actually using that kind of a feature engineering for specific and generic concepts in a data set to build a natural language understanding system. What they do is they do introduce domain information here in representation of an utterance and train an LSTM model. And also they train a generic LSTM model, so domain-specific and generic LSTM model to actually predict what the slot of a word would be. So remember, slots are a word classification task. training these kind of models where you would learn from unsupervised or unlabeled data sets. In this case, it's not unlabeled, you would need the domain information, but still, some kind of an information plus some unlabeled information or learning from the contextual information helps you improve your spoken language understanding as well, is what they are proposing. There's also this work which may be close to, can be considered as a multi-agent or like hierarchical model. They use this Gaussian process reinforcement learning algorithm to learn a dialogue policy for each of those domains. And then there's a committee model that predicts which of, given an utterance, which of these domains win, and then take the action based on that given policy's response. And the commission machine can be, an estimator, rule-based, what have you, but this kind of a model is a sort of can work well for composite tasks as well. And they show that this kind of, committee-based models are much better than if you train these individual models and try to predict the user's response based on each individual model. Okay, so to just give you another perspective to this graph is like looking at the dialogue depth. So the knowledge-based systems are the lowest to this to the dialogue systems. Then comes the common sense systems, and then at the very top is the empathy or the empathetic systems, where you would sort of want to, while you're conversing with an agent, to have some empathy or to have some understanding. And we've seen some examples of that throughout this talk of how an agent would behave like a human. But they don't, but we'd like to think they are. So there are some studies, for instance, they looked at this high-level intention spans, like for instance, assume that you want to reserve a restaurant, you want to check the location, you want to, ask your friend about it, or maybe during this time you want to play music, or maybe not music, maybe it's not related. So you want to find out that what kind of apps that while you're just doing some task is related to your task. It doesn't directly need to be related, but it is related. So an agent, so you can build an agent that actually knows and asks you questions. Like for instance, you're reserving a restaurant, the agent might say, oh, do you want to invite your friend? So should you want to contact this check the location, maybe there's traffic. So you want your agent to be your agent, like a human agent. And last not but least, there's this empathy in dialogue systems that have been investigated. What these folks have looked at is they have built extract information from the speech recognition engine. They extract information from the language modeling agent, but they also look at, while conversing with the human, they look at their facial information just to understand if the person is frustrated or if they are satisfied with it. So it's kind of an indication of how your dialogue model is going, and that's actually a signal to the system to reply back, oh, maybe they're not doing good, so maybe they want to confirm their action. This could be task-oriented, non-task-oriented, like a chit-chat oriented system as well. So, there's this one which we actually recently added. We've seen dialogue models being used for guess what kind of a game. In this game, the user is actually asking the system whatever object is. So they pick an object and they want the system to predict. The system actions are actually very simple, yes or no, but the system replies back with some questions. So this kind of the reason why I'm just presenting this here is that you could use not just the image but also the information that the user provides within the image to be able to make an have a natural conversation with the system. And all of these things that you've seen in the text and the image are used as features to build this kind of a dialogue engine. In conclusion, we have talked on dialogue systems, especially using the deep learning systems. You know, it is just the components that you have seen in building these dialogue systems can be built individually with deep learning algorithms. Most state-of-the-art technologies are based on DNNs, but you know, there's also some context or history or window of history has been used in many of the dialogue components that you've seen in this work. We've talked about how you would use deep learning models to do domain adaptation, especially for fast learning a new domain or learning new intents or what have you, even if it's a rule-based system or a rule-based agent. There are things that we have not touched on, but which are actually important, is what the reasoning. Maybe the empathy models might help to teach the systems to do reasoning. There's a lot of work that we missed out, but we've talked a few of them that used unstructured or human-to-human conversational data without any labels to construct user simulators or other models, other components of the dialogue system to lift up one domain that will learn to communicate with a user. And you know, we are actually going towards getting really good accuracies on many of the task-oriented ones. And as we have mentioned throughout this tutorial, although we have only mostly talked about task-oriented and a little bit about chat-based systems, there is a new trend where Dilek was actually mentioning this earlier, that those systems are getting closer to closer. Given a chit-chat environment, actually the system is trying to fulfill a task for you. So you would want your system not only fill a certain task, very quick restaurant restaurant reservation task, but also be able to help you to do other tasks, or maybe just talk to you and make your day better. So I suppose I've talked quite a lot about the conclusions, and we would like to thank these folks here that have gave us their slides and all the discussions that we had with them in preparing these slides, and I suppose there are our collaborators in one way or another. Yeah. Thank you so much for attending the tutorial. I suppose we're on time. I think we have a reception at 6, but we will stick around for 5-10 minutes to answer any questions that you might have. I know it's the end of the day, you're tired, maybe hungry, but we will be here. Yes. Yeah, would you like to use the microphone, because people want to hear the questions? Okay, yeah.
It's okay, yeah. So my question is, so she just talked about the user simulation studies where the structural constraints were encoded as a rule-based system that actually helps the system to explore the policy space, right? Is there any work which actually uses the output of the RL in order to improve, take some kind of feedback and add more constraints in the rule-based system?
There is work. Oh, sure, yeah. I don't recall on top of my head that would. Do you guys Unpublished maybe, yeah, but
and
it's an interesting question, but I don't know.
and my just a follow-up question would be like, would that be a MDP at all? So
if you do that
touch
loop?
it won't be MDP, and it's better to frame it as a GAN, I guess.
Well, you know, like especially for training reinforcement learning agents, you look at your current state and the previous state. So there's this like, or maybe a history of states. There's this window, and to make it more NDP, you need to have that state representation. So as long as you keep your state information, not just look at the current state, but also the previous state and the next state, so that you can get all the rewards, accumulate all the rewards. You might, but I'm not quite sure because I haven't seen, or maybe I'm not understanding your question correct, but yeah. So there's a question here.
Yes, so for people interested in natural language generation, last year in INLG there was a tutorial on deep learning for generation, and the example code is available online and is on dialogue systems. And I took that tutorial, and the amount of data was atrocious, and the system had only 3 semantic slots. So
it's probably human-to-human data. Collecting human-to-human data is actually easier, as you can access.
It was semantic-based.
Is it semantic-based?
So it really looks like it was generated from a little grammar that just produced all the possible encodings of those slots. So my question is, well, is that the actual state of the art? Because that's like 2 hours of work of writing.
Are you asking for NLG specifically?
Yes.
I don't know the NLG part that well. Maybe you might answer.
Can you repeat your question?
My question is, since last year tutorial, have things improved? Because I don't see much value of those deep learning models from semantics if they need so much training data.
So let me repeat the question. The question is, so he's been in this tutorial where there were a lot of data, but it was on semantic, frame base. He didn't see that much of a natural language based for generation task to be able to use the deep learning models. He says, is there any new work that actually have changed since last year?
I think there's a little bit, but I don't think the large improvement, and I guess the current issue is about the evaluation, because if you use the objective evaluation, it's a little problematic, right? And if you use the human judgment, it's not fair to compare with the other system if you do not have the same human judge.
Thank you.
So I think the semantic-based NLG, the previous, like last year or the last year one is I think the standard way to do the system. Yeah.
Nothing much changed, I suppose.
So what's your question?
Can you get close? We can't hear.
Okay. Actually, I found
One more question.
Sorry. Yeah, I found the usage of the user simulator is quite interesting, but I'm somehow feeling that the variation of the language that simulator can generate is somehow limited. For example, if the simulator is rule-based, it will be limited by rule. Yes, data-driven, it will be limited by the training data. Is that true?
That's true. So the user simulator is actually for training a policy network that has not been trained before. But once your policy network actually reaches to a point where you're sort of satisfied, you just drop your user simulator, maybe continue training your model using humans. That way you actually know that you introduce variation into your model better because you have the language understanding component, and you don't have to use an NLG component. So that's how people have been building their reinforcement learning agent dialogue systems. I don't know if you guys want to add anything here.
No, not really, but unfortunately we need to give away the room. So thank you for participating. We will be here for an additional 10-15 minutes. Please do come and talk to us because we need to close the room. Thank you.